So, in the last lecture I had gone through the separation of variables procedure for solving for the temperature field, the unsteady temperature field in a cylinder, and I outlined the procedure for you. The equation was the unsteady heat conduction equation written in scaled form. Okay. As T goes to infinity, the temperature goes to 0 and therefore, the steady temperature is equal to 0. And what that implies is that in our case the total temperature is the same as the transient temperature. Boundary conditions at r is equal to 1 in scaled coordinates, T is equal to 0. At r is equal to 0, the derivative is equal to 0. As you can easily verify, both of these are homogeneous boundary conditions. Okay. Either the temperature is 0 or the derivative is 0 at both boundaries. Okay. And the homogeneous boundary condition is essential for reducing the problem to the form of orthogonal for the orthogonality relations that will be used later on in the separation of variables procedure. In this particular case, by coincidence, the total temperature field did have homogeneous boundary conditions. In case the total temperature field does not have homogeneous boundary conditions, we have to subtract out the steady solution in such a way that we get the homogeneous boundary conditions. So, express the temperature as the product of r and the product of time, two functions, one which depends only upon r star and the other which depends only upon time, and substitute that, divide by f times g. Left side is only a function of time, right side is only a function of r, both have to be constants. That constant has to be negative, so that g decreases to 0 in the limit t goes to infinity, and then we get this equation for f of r. Okay. I had rescaled it by writing r beta times r is equal to r plus, and then the equation that we got, the equation that we got was only in terms of r plus, because the first two terms were equidimensional in r. So, if you multiply r by some constant, the first two terms on the left do not change. Therefore, I can rewrite r as r plus is equal to beta times r star, and then I get an equation that is only in terms of r plus. And I told you that this is in the form of a Bessel function with n is equal to 0. The Bessel function has this general form, but for the particular case n is equal to 0, you get the same form as the equation that we got for f using separation of variables. And therefore, the solution for f is given by this. This is the solution for f. And the solutions j0 and y0 I had plotted for you, j0 of x and y0 of x. Each of these passes through 0 multiple times as x increases. j0 has 0 slope at x is equal to 0, and then it oscillates multiple times. The amplitude of the oscillation decreases as x increases. The spacing between successive 0 crossing increases. y0 in contrast goes to minus infinity as x goes to 0. It also has oscillations. It crosses 0 multiple times, and the amplitude decreases and the spacing increases as x increases. So, they have common features, both of these functions. The big difference is that j0 has 0 slope at the origin, y0 goes to minus infinity, and therefore, the slope is infinite at the origin. The symmetry boundary condition was that the derivative of f has to be equal to 0 at the origin, and that is satisfied only if the coefficient b in this equation is equal to 0. So, therefore, I got the function f as some coefficient times j0 of beta and r. The total solution is the product of f times g, where both f and g have the same values of beta n, so that in my separation of variables procedure, the left and the right sides are equal. This solution satisfies the equation for any value of n, the boundary conditions for any value of n, because both boundary conditions are homogeneous. So, it satisfies the boundary conditions for any value of n, which means that the solution for the temperature profile is the sum of these functions for n is equal to 1 to infinity. Note that I have started my index beta 1 at n is equal to 1, where you have the first 0 crossing of j 0. So, now these coefficients have to be determined from the condition that at t is equal to 0, t star is equal to 1. Okay. They have to be determined from the condition that at t is equal to 0, t star is equal to 1. And here, as I told you, we can use the orthogonality relation for j 0. That is, if I have functions j 0 of beta I r and j 0 of beta j r, both of these beta I and beta j satisfy the homogeneous boundary condition. That is, j 0 of beta I is equal to 0, it is a 0 crossing, and j 0 of beta j is also 0, it is also a 0 crossing. Then if I take two such functions, multiply them by each other, integrate from 0 to 1, the integral is 0 if I is not equal to j. Okay. The integral is 0 if I is not equal to j. It is non-zero only if I is equal to j. Okay. So, that condition exists for the orthogonality relation exists, provided I do the integral of j 0 of beta I r, j 0 of beta j r multiplied by r dr, okay, provided I do it multiplied by r dr. Okay. Since I have this orthogonality relation, okay, I can multiply both sides by j 0 of beta j times r, okay, multiply both sides of this equation by j 0 of beta j times r, integrate both from 0 to 1. Okay. On the left side, it will be non-zero only when I is equal to j, okay, and I can get an analytical result. This result can be found in standard tables. Okay. I will not go into the calculation, that is a subject for applied mathematics, but you can show that this is non-zero only when I is equal to j. The right side also has an analytical result, okay, and therefore, from that you can find out what is the explicit solution for A. Okay, I can find out the explicit solution for A. Okay. And from this I can find out the solution for the temperature profile. Okay. From this I can find out the solution for the temperature profile. So, how does this solution look? Okay. How does this solution look? Okay. Beta I is a discrete value. Okay. So, I can even though the summation is from 0 to infinity, I can get an analytical approximation by taking a finite number of terms in this series. Okay. I can get an analytical approximation by cutting off the series at a finite number of terms. And beta I monotonically increases as I increases, because beta 1 is the first 0 crossing, it has the smallest value, beta 2 is the second 0 crossing, it is higher, beta 3 is the third and it is still higher, and so on. Okay. That means that e power minus beta I square t decreases as I increases. Okay. Therefore, this exponential term here decreases as I increases. Okay. Which means that I can get a good numerical approximation by truncating this series after a finite set of terms. Okay. And then I can examine how the actual solution compares with the analytical approximation. Okay. So, in this case, let me plot T star, okay, versus R star. Okay. This is R star is equal to 1, okay, where T star has to be equal to T star has to be equal to 0 at this location. T star has to be 0 at this location, and then you have at different values of R star, okay, the temperature profile for different values of T. okay, for different values of t star. Okay. So, I will consider 3 cases. Okay. The first is t star is equal to summation I is equal to 1 to 5. Okay. I include 5 terms in the series. Okay. Okay. The second is where I include 3 terms. Okay, 3 terms, each of those terms correspond to a beta that has a 0 crossing. Okay. J naught of beta I is equal to 0. Okay. In the third term, I just include one term. Okay, that is 2 by beta 1 j 1 of beta 1 . Okay. When I include 5 terms in the series, okay, then for T star is equal to 1, I get, okay, the temperature is virtually 0 throughout. Okay. So, this is at T star is equal to 1. Okay. It has already reached steady state at T star is equal to 1 and the temperature is a constant throughout, and that constant temperature is actually recovered by all of these. Okay. Both the 1 term expansion and the 3 term expansion, both of these give you the same value, that it is virtually equal to 0 throughout. Okay. So, let me put here T star is equal to 1. Okay. That is the value, that is the initial value. Okay. That is the initial value, and by the time this temperature, the time is equal to 1, okay, the scale time is equal to 1. When the scale time is equal to 0.3, okay, I get a small value for this temperature throughout the domain. Okay, it goes something like this. Okay. And once again, both approximations get, okay, the temperature correct, okay, at T star is equal to 0.3. Okay. At T star is equal to 0.1, you start to see some difference. Okay. At T star is equal to 0.1, okay, you start to see some difference. This is the total solution. So, let me, okay, this is the total solution. This is the 5 term series. The 3 term series gets it on, okay, numerically, okay, identical. The 1 term series has some difference. Okay. The 1 term series has some difference. Okay. This is at T star is equal to at T star is equal to 0.1, the 1 term series has some difference, but the 3 term and the 5 term series are almost identical. Okay. Now, at T star is equal to 0.03, okay, at T star is equal to 0.03, the complete solution, the 5 term series, more or less gets the temperature close to the surface, okay, and then, okay, it decreases to 0 at the surface. Okay. So, the 5 term series is numerically accurate. Okay. The 3 term series is also reasonably numerically accurate. Okay. The 3 term series is also reasonably numerically accurate. Okay. However, the one term series is not in agreement. Okay. The one term series, okay, if you include just one term, it will not be in agreement. Okay. Okay. The including just one term in the expansion gives you a wrong result. Okay. It should not, it's not like that. Okay. This is at okay, T star this is at T star is equal to 0.03. Okay. And at T star is equal to 0.01, okay, the 3 term expansion still gets, okay, I am sorry, the 5 term expansion still gets the temperature to be a smooth function. Okay. The 3 term expansion is not in agreement. Okay. So, it goes something like this. Okay. The 3 term expansion is not in agreement, and the 5 term expansion and the single term is further away still. Okay. The single term is further away still at T star is equal to 0.01. Okay. So, you can see that the up to 0.1 a single term gets the solution quantitatively accurate. Okay. Until 0.03 the 3 term gets the solution quantitatively accurate, and at 0.01 you require 5 terms in the series in order to get the solution quantitatively accurate. Okay. So, even just including a single term you can get a solution down to T star is equal to 0.1. Including 5 terms you can get it down to 0.01. Okay. So, those are the comparison of the single term approximation, the 3 term approximation and the 5 term approximation for the solution, okay, of the temperature field. Okay. So, clearly the separation of variables solution with even a small number of terms in the expansion is giving you a quantitatively accurate result when time increases beyond about 0.03 or 0.01. Okay. When time is very small, it breaks down, and the reason is because you are trying to so at very early times, okay, at t is equal to 0, for example, okay, if I just plot at t is equal to 0, the temperature profile actually is a step function. Okay, it looks like this. Okay, the temperature profile is a step function. Okay, it looks like this. Okay. What you are trying to do is to write the step function as the sum of a series of functions. Okay. Okay. As a sum of a series of functions. Okay. Each of which represents, okay, one of these segments. Okay. The first one represents the segment going from 0 to 2.405. Okay. It represents one of these segments. Okay. So, you are trying to represent it by a series of functions, okay, the first of which looks something like this. Okay. This is r star. So, okay. The second one looks something like this. Okay. The second one is this segment, okay, which has a 0 crossing here. So, the second one will look something like this. Okay. It has 0 crossing there. The third one will have 3 extrema. Okay. The third one will look something like this, and so on. Okay. So, you have this infinite series of functions. You are trying to express this step function or something that looks like a step function in terms of this infinite series of functions. So, obviously, you need a very large number of terms to get it accurate. Okay. For very early times, let us say t star is equal to 0.01. Okay. However, at later times you do not have this problem, because just a small number. So, because the temperature profiles are all smooth functions and you are trying to represent them by a series of such functions, and you can see that by the time T star is equal to 0.1 in this figure, say, okay, the profile actually looks very similar to just the first function. Okay. So, you need to include just the first function when the temperature, when the time exceeds, okay, 0.1 times the diffusion time. Okay. After that you can get an accurate representation even with a very small number of functions. So, what do we do at very early times? Okay. What do we do at very early times? Okay. Let us see physically what is happening at very early time. Okay. Okay. I have a cylinder, okay, and in scaled coordinates the radius is 1. In scaled coordinates the radius is 1. Okay. And I want to find out what is the temperature profile. This temperature initially was T star is equal to 1. It was immersed in a fluid with T star is equal, with temperature T star is equal to 0. Okay. At very early times, the change in temperature due to the application of the boundary condition is going to be restricted to a thin region close to the interface. Okay. It is going to be restricted to a thin region close to the interface, okay, of thickness, okay, of thickness which is small compared to the radius of the cylinder, okay, of thickness small compared to the radius of the cylinder. Okay. That penetration depth, since it is small compared to the radius of the cylinder, it cannot depend upon the radius of the cylinder. Okay. Therefore, the penetration depth, okay, the penetration depth is going to be will be square root of alpha times T. Okay. The penetration depth will be square root of alpha times T. Okay. The ratio of the penetration depth and the radius is going to be equal to square root of alpha T by r square. Okay. Alpha T by r square is my scaled time. Okay. Is my scaled time. Okay. So, when the penetration depth is small compared to the radius, then I will have T star being small compared to 1. Okay. When T star is small compared to 1, the penetration depth is small compared to the radius. Okay. So, basically at the surface of the cylinder for a thin region, okay, adjoining the surface of the cylinder is where there is a change in temperature because of heat conduction from the surface at very early time. Okay. That is where there is change in temperature because of heat conduction from the surface at very early time. If the thickness of this region is much smaller than the radius of the cylinder or the radius of curvature, okay, in this case it is the same as the radius of the cylinder. If the thickness is much smaller than the radius of the cylinder, then the temperature profile is similar to heat conduction into an infinite flat surface. Okay. If the thickness of the cylinder, if the thickness of this region is much smaller than the radius of the cylinder, locally it looks like conduction into an infinite medium. Okay. Locally it looks like conduction into an infinite medium. Okay. Okay, where the temperature as a function decreases, okay, as r goes to infinity. It starts at T star is equal to 1 and T star is equal to 0 far away. Okay. And therefore, at these very early times you would expect the solution for the temperature to be the same, T star is equal to 1 minus error function of psi that we had already obtained. Right, because if the thickness is much smaller than the curvature, radius of curvature, then it resembles the conduction into an infinite medium. Okay. Effectively, it resembles the conduction into an infinite medium, and this is the temperature, okay, where psi is equal to 1 minus error function of z by root alpha t, okay, where this is the coordinate z. Okay. That z coordinate expressed in terms of this is this one. Okay. Therefore, this z coordinate is equal to the total radius minus r. Okay. Z is equal to the total radius minus r. Okay. Or I can write this as r into 1 minus r star. Okay. That is the z coordinate, r into 1 minus r star, because r star is the radius divided by the cylinder radius. Okay. So, that is the distance from the surface. Okay. That is the solution for the temperature profile for a unidirectional transport into an infinite medium, where z is the distance from the surface. Okay. So, I can write this as 1 minus error function of r into 1 minus r star by root of alpha t. Okay. Let me write this as star. Okay. And we know that, substitute this expression. Okay. The denominator alpha t divided by r square is just t star. Okay. So, I can write this as 1 minus error function of 1 minus r star by square root of t star. So, therefore, this is the solution I would have at very early times. Okay. And now I can plot this as well. Okay. I can plot this as well as a function of r star. And if I plot the actual temperature profile that I get in this case from the 5 series approximation at T star, okay. So, this is T star equals 1. Okay. If I plot the actual temperature profile that I get from the 5 series approximation, okay, at T star is equal to 0.1, okay, I get something that goes like this. Okay. And if I plot this solution, okay, I get something that is almost spot on. Okay. If I plot this solution, I get something that is almost exact. Okay. So, this is at the very early times T star is equal to 0.01, where this separation of variables solution with 1 and 3 terms was not agreeing. Okay. At T star is equal to 0.01, okay. This separation of variables solution using 1 and 3 terms was not agreeing with the 5 term approximation. The 5 term approximation was relatively smooth and it was close to the exact solution. The 1 and 3 term approximations were not in agreement. Okay. Whereas, if I plot this similarity solution at very early times where the penetration depth into the cylinder is much smaller than the cylinder radius, then I do get something that is in good agreement. Okay. The agreement is not as good even at T star is equal to 0.3. Okay. So, at T star is equal to 0.3, the 5 term approximation looks something like this, whereas the similarity solution actually has a slight difference. Okay. This is at T star is equal to 0.03. Okay. So, the similarity solution does not agree with the 5 term approximation from separation of variables or the exact solution even at 0.03, but it is in good agreement at 0.01. Okay. So, therefore, for very early times you can use a similarity solution here as well. Even though it is not an infinite medium, when the penetration depth is much smaller than the radius of the cylinder, you can consider it as an infinite medium, and use that similarity solution in order to get the solution for the temperature profile. So, this is the solution of the separation of variables solution and the similarity solution put together for heat conduction in a cylinder, separation of variables for long time, similarity at very early times. These will give you good approximations for the actual temperature profile in the cylinder. In the next lecture, I will cover one other aspect, and that is the orthogonality relations. I had showed you in the case of a Cartesian coordinate system how the orthogonality relations emerge. I will do the same thing for the cylindrical coordinate system in the next lecture, so that we know why, when there are homogeneous boundary conditions, the solutions turn out to satisfy orthogonality relations, and for that reason we are able to actually get analytical solutions in which the coefficients can be explicitly determined. So, this last bit I will cover in the next lecture. I will see you then.